Hi there, and welcome to the third topic. This is going to be very interesting. If you've gone through the 4.1 and 4.2, we're going to have some more fun here now. And then let's see how we can put together what we have learned in 4.1, 4.2 and come up with a very nice technique. I call it the decision table based testing. Ideal would be to jump into an example that can give a very effective method and concept of learning. However, let's look at how we take decision tables as a technique. And in fact, this is a technique that is used by us even intuitively. Even if without such technique that we're going to learn today, you would still look at combinatorial yourself intuitively. This is something that comes by intuition to most of the human beings. Very clear, this is one of the most systematic approaches. And you would agree once we have looked at how we go through this particular technique. It has a logical rigor. In fact, there is a clear basis for decision table is the logical rigor. And this is where the propositional logic that you would have learned, and in fact, you would have revised it in the formal methods and mathematics for testing, that would be useful over here for decision tables. The better you know the logical rigor and the methods to bring in that rigor, decision table will start becoming as much effective. There is another graphical method which is known as cause-effect graphing. We're not going to really look at the cause-effect graphing as a technique. It's one of the old techniques, generally not used these days. If you would specifically wish to consider learning, because many a times graphical techniques are useful at the desk, in fact sometimes to explain as well. So this technique is like the flowchart. Now it's really becomes a choice of people who really wish to use flowcharts. If you ask me personally, I'm a lover of flowcharts and also the cause-effect graphing. So if you wish to look at cause-effect graphing, you should look at the book by Binder for object-oriented testing. It does have a chapter which focuses on cause-effect graphing. And also one of the classic books by Myers that also provides a chapter on cause-effect graphing. The next one is about what is this technique ideal for? We are looking at combinations. Whenever there is a combination, whenever we are looking at one and one combined, that is where this technique becomes very, very useful. And then all said and done, we are going to work on certain creation of rules and test cases and scenarios. One way to look at it is pause at this time, take a pause, don't go ahead for the video. What you can look at is for any of the work on testing that you would have done, in fact, any development that you would have done, which requires combinatorial work, maybe that is something that you should bring for reference for the remaining part of this particular topic. And as we start looking at the technique, you may want to apply it to that particular problem that you're solving at your desk by considering the simple example that we look at right now. So both would go hand in hand. So that's an opportunity that you have. So let's proceed. Let's look at what this technique really means. What is the template of this particular technique? So what you have in front of you is a table. So what we're going to call here are, these are the set of conditions. These are actions. And these are a set of rules. If you have observed, we have 8 rules. They correspond to the number of conditions. So this is equivalent to 2 raised to n, which is in this case 2 raised to 3, which is equal to 8. Each rule defines a combination of conditions which are represented as true, false, or don't care. We further include blank, which is not applicable, specifically to define certain rules for us. So true false would mean that condition C1 is true, condition C2 is true, and condition C3 is true. All three have to be true for this action to take place. That's how we start defining. And now you know why we get 8. And the moment we have a don't care, you collapse those many number of rules. Because this rule would mean that C3 exists, C3 has to be there, but we do not care about it. It could be either true or it could be false. Same is the case over here, true or false, which helps us collapse the number of rules. Because rule 3, 4 becomes same. Rule 7, 8 becomes same. Now, potentially, each of these rules can lead to a minimum of one test case. So each rule leads to one test case minimum. It could be many more, depending on what this rule is all about. A condition could include multiple things within it. If my condition is that individual is a senior citizen, then I'm looking at age, and I'm looking at age which has bounds. If I'm looking at adult, then I'm considering and defining adult as any individual above 18 years. And if I have a senior citizen also defined in my problem statement, I'm going to keep a limit probably of 60 years. So anyone from 18 to 60 would be considered as an adult, and that is a person adult or no could be C1. So I may have C1 which is equal to adult and question mark, could be true or false. In that situation, the condition refers to age. If I now combine and say we are looking at adult male and adult female, our further condition would mean that I have now age and gender come into play. If I have age and gender that comes into play, thus C1 just being true and false is now making up a combination of inputs that can become my frame. And if you look at our 8-step method, now you would start correlating how decision table technique can also be derived very well out of that thought process. So you understand the logical rigor part over here. This also provides a notion of completeness. We care about completeness and coverage. So completeness and coverage becomes very nicely done when I'm pretty sure that all my conditions are taken care of, my actions are visible, that is my outcomes, and the rigor that comes in because of those rules, all of this gives me a notion of completeness. Needless to say, logical rigor built into it. The other after effects, byproduct of such an organized mechanism is if one of my action changes, if A3 is going to change as a requirement, I exactly know where lies the impact, because I would have now known the impact. Or if my condition is going to change and behave differently, I exactly know what is going to be the impact on the action and what needs to change, which test case needs to change. So this provides me a built-in traceability. And in fact, a pictorial view like this, of course, if you have thousands of such rules, it would be difficult to create a pictorial and tabular form which is viewable in one view, but still it provides me a opportunity to create a pictorial view where I can get a systemic view. And that is where breaking down becomes important. I better not have a stub which has 50 inputs, 50 such conditions. It might become manageable only using a computer, because computation would be required to manage so many rules. Now, if we look at the fleet management solution that we looked at, maybe I definitely need a computer and computation to manage so many number of combinations. Thus, you will appreciate that right from a simplest of the technique, we start looking at how huge it can get. To enable us to understand the details of the technique and also the appreciation towards the applicability of such a strong technique, let's look at a simple example. Take a minute over here right now, pause the video at this slide and read through the entire example that we're going to look at. Okay, so now that you have read, let's look at the specification for this component and we'll look at it from a test spec perspective. First character must be A or B, second character must be digit. Two things that come to us. Then, based on some condition, we have got a file being updated, which is an action. So I have an action over here. This is an action. Message is an action. Message is an action. And then this becomes my condition. Again, take a pause. Look at the desk example that you had. If you have got one to this particular class, let's look at that example. Take a pause, understand how such kind of test spec of conditions and actions apply to what you have got. Okay, let's drill deeper. And our problem is develop test cases using decision table technique. So we'll now go deeper, and in fact, I'm going to blow it up and show you the solution that we have. We came up with a solution over here. There are two ways to look at it. One, pause right now, understand what has been done, or proceed in a similar manner and understand through the explanation. So here is how we built the conditions. We built the conditions. C1 is first character is A. C2, first character is B. And C3, second character is a digit. This is what came to us from the first two statements. This is where my conditions came in. Now remember, if you have paused and actually put together the conditions, you may have come up with a condition which says first character is A or B. The moment you have put in first character is A or B with a true or false, you may not be able to represent all inputs. So remember, when I say first character is A, presence or absence of A can be determined by true or false. But if I say first character is A or B, either it is A or B or it is a non-A or B character. So you can imagine what you need to represent. The other piece is what I need to represent could also become an equivalence class. Character A and B become one class and non-A and B becomes another class. That is valid and invalid subdomain represented digitally in a decision table through logic. I think appreciating that depth would allow you to understand how representations of conditions can be done. So that's how the char is A or B is not considered, but we have got first character as A and second character as B. The third condition is second character is a digit. Now the actions. File is updated. You would recollect that file is updated as an action. Message displayed. And this is something that, okay, it could also become impossible. One of the impossibilities is first character is A and first character is B, both true, is not possible. If I now remove all the impossible, I know how much I need to pay attention to the possible ones. So that means I'm reducing to begin with. This helps me reduce. And we have written all the 8 rules. 8 rules as true, true, true to false, false, false. And I'm sure you definitely know how to come up with those rules. So first character is A, second character is A, both true is not going to be possible. So I've got an impossible piece over here. So that is the impossible. There are 2 impossible ones. First character is B. Second character is a digit. My file is updated. First character is A or B. So that is I've got this is true here, this is true here, and I've got second character as a digit. My file is updated. I look at my error scenarios. These become my error scenarios. And I've got scenarios where desired outcome is happening. This is how I come up with rules. The test cases which are marked in a different color, or the rules that are marked in red color right now, you'll not be able to simulate them at all. So this do not become test cases at all, if I consider every rule as one test case. So test case 1 comes out of rule 3, which is A5. First character is A, it has to be A. Second character is a digit is false. Now second character is a digit is false could mean that it is a non-digit. Now for rule 4, I chose to make it as AC here. But remember, it is going to be first character is A. So it has to be A. But the second character is a digit is false could mean anything. It could be any input out of those hundreds of characters. It's not millions of characters, out of those hundreds of characters. Or at least thousands. If I'm looking at, I could even enter Chinese or Japanese, which are very picture form of languages. So if I look at those, there are more than one test case out over there. So every rule need not be one test case only. It could be more. And such an example is a very typical example of how the file names in a camera are sometimes constructed. You would have a date, time, and then there is a combination that comes into play. Or IMG is added, or DSC is added. So such is the way where we have got this technique called decision table based testing technique. I hope you liked it. And also the problem that you have got from your desk, I believe you should be able to solve it more effectively by using those methods and also the technique, and also believing that how combinatorial can be useful. The key areas to look at is, how do you come up with these? Actions are easy, but how do you come up with these conditions? That becomes crucial. One of the very classical problems to solve is around combinations of inputs that are required for a car to start. fuel, battery, they become true or false. And then you know when the engine is really going to start. So a lot of these digital inputs or combinatorial pieces would make sense. It would also mean that we can look at an analog system converted to digital. Let me explain what I mean here. The temperature in this particular studio is maintained to a certain level. Now I'm sure there is an evaporator, a chiller running to condition the air, to cool the air before it is pumped inside. It is set at, say, 22 degrees Celsius. Is the temperature 22 degrees Celsius? If yes, then the compressor is switched off. If no, then the compressor is running. So you know that the temperature is going to be an analog input, but it's actually compared with a value and then we make it digital input. So a lot of these things become very useful when we are looking at testing such a system. Later as we go along, you would find that there are examples which are around building lighting control or your day-to-day examples. Imagine one of the best day-to-day example is a traffic light. At a traffic light, a lot of combinations need to exist. Largely it is timer input. In Indian conditions, it's timer input. Now look at in some of the traffic lights in the United States and in Europe, you would typically find that there is a pedestrian input. Typically someone wants to cross the road, they would come and press a button, and with that button, the system knows that there is a pedestrian who wants to cross and hence will make room in the timing for a pedestrian to cross. Because some of the cities, some of the towns are sparsely populated. There are not many people who would want to cross every time. Thus, when there is nobody who wants to cross, you don't want the traffic light to spend time for pedestrians. Largely efficient, isn't it? A timing analysis of our own digital systems could help us understand if there is a wastage of a resource. So a lot of analytical inputs and outputs can come out of such kind of testing and such kind of analysis. So you remember that test specification and requirement specification, when they are learned, when they are analyzed, there are a lot of byproducts that come out for a particular system. For example, you look at the movie Apollo 13, right? If you're looking at Apollo 13, there is a lot of on-off that goes on. There is a sequence of things that needs to happen for that particular module, the lunar module, to do something. Amazing, isn't it? How would that be tested? Similarly, a lot of things need to go in that kind of testing, and this technique just allows that rigor, that logical rigor. Thus, I hope this is very useful for you and you enjoyed learning it. And in the next topic, we will look at some of the examples a little deeply, some day-to-day and some complex. Thank you.